Yeah, so we should get started. So welcome everyone. We're happy to have Shammur from QCRI, and she did her PhD from University of Trento, if I remember correctly, and then she also did a postdoc, subsequent postdoc in the group, and then now she's a research scientist in QCRI, and she's going to talk about probing methods and ways you can interpret end-to-end speech models. And it's a very broad class, and you will learn a lot more. All right, Shammur, the floor is yours.
Yes, thank you. I'm expecting actually to learn from here too. So hi again, I'm Shammur, and today I would like to focus my talk on how to analyze the encoded representation in our day-to-day, let's say day-to-day and speech models. And this we want to do via the simplest technique called probing neurons. So over past around 5 years, end-to-end models, not 5 years, 7 years, I think, or more, end-to-end models has been pushing the boundaries of NLP speech and other spheres of AI. So looking into the success of, let's say, ASR and all the new exciting self-supervised speech representation models, we can see not just how end-to-end improved the performance of this model, but it also at the same time provided flexible training recipes that any one of us, like if we want to start training a model with little linguistic or any background knowledge, phonetic knowledge, we can do it. So this simplification is great because it attracts a lot of people. We are learning quickly, creating more models, but it comes with a huge cost, right? These models are largely black box. We don't know what information we're learning and how this information they're using during their prediction task. So this black box strategy actually brings a lot of unanswered questions. And for last 5 years, I think there are huge amount of work that aims to decode what these black box are learning. Speech let's say in the field is not new, like for interpretability, but it's very essential to understand what's going on in a speech model, because speech is primary, but yet it's a complex form of communication. Every attributes like the speaker information, language, everything impose a different characteristics on the acoustic signals, making these signals unwanted signals, let's say, available to the network. So our goal here to analyze this encoded information in the network using neuron level analysis. For better insights, there are many methods that has been tried out in the past. Among them, visualization of the activations of the neurons and manually identifying the patterns is one of the popular way to go. But using visualization technique, it is not always easy to interpret the findings, and such technique is also difficult to understand when a neuron is shared among different properties. So for which property is this neuron is activated is not, there are some difficulty to interpret. So there is also other approach apart from visualization that includes clustering neurons to uncover some novel properties that's not let's say human defined, or sometimes to find general redundancy in the network that, okay, this cluster of neurons includes same sort of information. So maybe they're redundant in terms of information. So so using this method, there has been a lot of work, as I was saying. So this brings out to the last method that I'm going to talk about. And this is actually the method of choice for this talk is neuron probing. Instead of looking into the data from data perspective, like what is the next token or how this sentence is activating the neurons, here we want to probe the model for finding particular property or concepts. Now, what I mean, for the predefined property, we want to see if the property is present in the network. If so, which part of the network is capturing this property? How this information or the neurons capturing this information is distributed in the network, and what is the minimal subset of the network that can post this information. So this will be the main objective of this talk. We will try to answer or see how to answer these questions. Now, so this is our overall experimental flow that we're going to follow. It's a very simple simple steps. What we are going to do is we are going to extract layer or block representation in case of transformers from the network and check if they captured the information that we are looking for. Here, the information or the properties is defined mainly, it can be by speaker information, it can be language, channel, content, paralinguistic like emotions and others. But for this task, these are the specific properties that we are interested in. Gender, speaker identity, mainly we will pose it as a speaker verification problem. Language identification, regional dialect. For this, we took 5 Arabic dialects. And of course, the channel of the, let's say, the samples data. And when we prepared this data, we made sure that all the classes are balanced. Language is constant. For example, whole data set over here is Arabic, so that we don't have any other gender bias or something influencing this data set. So it's a very controlled data. As I was actually talking beforehand, that the probing mechanism that we are using is largely model agnostic, but here we want to test our system on 4 models, 2 end-to-end model trained via supervised objective like dialect identification. We have 17 dialects over here, very fine-grained dialects, and the speaker recognition using voxel1. It's a very well-known models and a simple architecture, 4 CNN, 2 FCs. Whereas we are also trying to see how model trained to reconstruct masked signals such as Mockingjay is also performing in this case. So we took 2 architecture, base, that is the 3 layers, and 12 layers of transformer encoders. So this is our choice of model. Then let's go to the method. For probing, we used utterance level representation. So we first extracted the frame level representation and then pulled it across the time axis to get the utterance level. And using this utterance level, we trained our proxy classifier for a certain property and for each layers. So for the probe that we trained, we use a simple logistic regression model by minimizing the cross entropy loss along with the regularization term. The probe itself is we hope, I mean, I'll evaluate that later, but reflects the strength of the encoded information, yes, but it also has the potential to identify the important neurons and help us to rank these neurons for its informativeness. So the choice of regularization for the probe directly affects how we rank. So for this task, we use elastic net regularization, where we use both L1 and L2 to exploit the sparsity effect of the L1 regularization, helping us to identify important individual neurons. At the same time, we are also taking into account of the groups of highly correlated features similar to L2 regularization. Thus, it gives us actually a very good balance of localization property versus distributed properties of the selected neurons. Sorry, excuse me. Now, how did we use these neurons to rank based on their informativeness? So first we take the absolute weights of the model per class, of course, and then sort them in their descending order. Then we start selecting top P% of neuron based on the cumulative weight of the total mass, and then start combining the sets of salient neurons per class. So then our ranked neurons is the overall union of all the salient neurons per class for P%. We start with P, very small amount of value of P varies like 0.1, and then we increment to increase to 100%. And thus we get a ranked list of the neurons. Now we first benchmark the probe's performance by considering the full neuron representative. This we called oracle performance. And then we compare or evaluate if the probe is actually representing the encoded information or it's just memorizing some whatever represent it's getting, or just relearning from the data. So for this, we perform few baselines. One is random initialization of the embedding. So we randomly initialize the representation instead of taking from the model. And second is called control task. We use selectivity as a criteria proposed by Huet in 2019, where we take the classes from our original data and then randomly distribute the instance, maintaining the distribution of the original class. And the idea is that using this, the difference between the oracle performance, that is the result representing using the neurons of the full network, and the result of the control task would be high. So the difference should be strikingly high. The more the difference is, the more reliable we can say the probe is. So here are some results. We notice that for most of the tasks, we have high oracle compared to the random initialization, also majority class, and our selectivity is pretty much high, thus showing that yes, the probe is not memorizing, and we can rely on its accuracy to represent if the information is there or not. Next, we want to test the ranking method that we proposed is effective or not. So for these, we perform 3 tests on our previously trained probe. So we have a ranked list. What we did, we first selected top or bottom or random 20% of the neurons from the ranked list and masked the rest of it. Then using this top, top 20% of the neurons, we tested our trained proxy classifier to find the accuracy. Our expectation was that the top and the top accuracy should be higher or close to random, and so is the random should be higher than the bottom. So if this is correct, that means our ranking is successful and it is actually capturing the informativeness of the neurons for a certain property. So here we mostly see the expected pattern in cases like this. For example, in gender, we see the top is 98.3, where random is 98.6, though it's very close over here. It has some other significance we can later see. And the bottom is 58. So with 20%, we have better results than the last bottom 20% of the neurons. That we also see same for the language, for the regional dialect experiment and such. So mostly the ranking is working, let's see. Now, here comes the main part of it. So what can we do this? We already have a method that we can use to probe. We already know how to rank the neurons based on its importance. And we have seen that the probe does reflect the strength of the representation, encoded representation. So this is something we already found, and let's say this is reliable. But how can we use it? Can we use it to see if the property is present and which part of the network predominantly captured this property? But we don't need to see neuron for this. First, we can just see the layer-wise information to see if this network is capturing this information. So mostly we notice that the voice identity and dialectal information are captured in their own task-specific networks. So for example, a network that was trained to identify fine-grained dialects is able to successfully capture the regional dialects that are, even though if they were not present in the original model. Whereas the speaker recognition model is successfully capturing voice identity, which is expected. But None other models, even for example, the transformer models is capturing speaker variant information, nor dialect variant information. Whereas for gender, for channel, we notice that this information are easily encoded and distributed throughout the network. The green ones is actually all the layer includes this information, and the red ones is actually localized in the upper part of the network. So we mostly see that the language are always captured in the upper portion of the network. So this shows if the information are there or not. Now, coming to the next point, can we see what is the minimal subset of neuron that we can extract is capable of representing the same information as the whole network? So before that, before seeing if it is able to capture it or not, let us see how we define the minimal neuron set. For this, we took our ranked neuron list and gathered p% of neurons from the list, and then retrained the classifier or proxy model until or unless the performance of the probe is actually within a threshold of the original Oracle model. So we keep taking p%, and when, for example, over here is within a threshold of, let's say, 1 or 5, I think for some tasks we use 5 within a threshold, we stopped training the probe, and we said this 20% of the neurons are enough to encode this information. So here are some results we have. We noticed that for most of the tasks, we can use only, let's say, 20% on average. Like over here, 5, 15, 10. This is different. For speaker recognition model, we see that 50% of the neurons actually encode and is needed to classify gender. This is actually something we have to again probe and see why. Apart from that, only let's say 5% of the ADI network, that is the dialect identification network, is needed just to encode gender classification, gender information. As for the language identification, we also see the same, that using only 20% of the neurons of a model learned to distinguish dialect is enough to encode different language information. Like here we use 7 language. So this 20% is enough. That means for language, other 80% of the network is redundant. If we see in case of, let's say, transformer with 12 transformer layers, over here, only 10% of the neurons of the whole network is needed to classify or encode gender information. Similar for the channel information, only 10% is needed. So this shows that how much redundant, I wouldn't say redundant, we have to test it, how much minimal amount of information is needed to capture, and what a waste of, let's say, rest of the model for this particular property. So using this, let's say, 20% of neurons, what we can tell about the task complexity, task specific redundancy, and other properties like shared information among the neurons. So we notice that the size of the minimal neurons can reflect the nature of the task and its complexity. For example, for encoding, as I showed earlier, for encoding gender and channel, we need handful of neurons in most of the architecture, like 1 to 5%. In some cases for channel, it's 10%. So which is very minimal. Is this a good thing or bad thing? That's another question. For example, in channel, do we really want our model to distinguish between what is the source of this, let's say, the audio information that we are giving? Is it from a high quality video, or is it from information that is just broadcasted or downloaded from YouTube? So this type of information is being encoded using handful of network neurons. Then we notice that for complex tasks, like for example, the voice identity I was talking about, it's actually presented in some specific network, not all, we need a significant amount of neurons to encode. So for example, for English, when we did speaker verification with the VoxLab1 test data, we noticed only the last layer, that is the FC2 over here, can encode the information. And when we probed this layer, just to see how much of the neurons in this layer are important for the task, we noticed 50 to 70% of the neurons are used in this case. So the information over here is not redundant, and every neurons are contributing to distinguish between speakers and speaker variant properties. So this is one thing that we wanted to see, that the size of the neurons does reflect task complexity, hopefully. The next thing is task-specific redundancy. Can we use this neural probing for finding task-specific redundancy? So before going into that, I want to explain how we define task-specific redundancy. For defining this redundancy, we use two criteria. First, we want the accuracy of the minimal set to achieve at least 97% of the oracle performance. That is, the oracle is the whole model using all the neurons of the network. So it has to be at least within 97% range of that performance. Plus, if we train the probe with random p% of network's neuron, the result should be within a threshold of the top p%. So with let's say the top 5% neurons should give a result that is within a threshold of any 5% of the neurons from the network. That means the information is redundantly encoded in there. So in this case, we see that, for example, gender classification task for ADI is actually, this information is redundantly encoded. 5% again, as I was showing, only 5% of neurons is needed to encode this information. When we train the probe, retrained, let's say, the probe with this 5% of neurons, we noticed we actually have a better performance compared to the oracle result. And then when we retrain, when we pick random 5% of the network's neuron, we find we actually get a close within a 5-point difference, 94.65 accuracy. That means even though the top 5% is most, let's say, informative, the other part of the network is also capturing the same information. And this information is so how should I say, easy to encode that all the neurons are capable of capturing it. Then we see actually same for channel. Even we see this in the language property for the ADI model, where with the oracle 86%, with only 20% of these neurons, network neurons, we can get 85.30 accuracy, and the random is gives us 82.40. So this shows that the ADI model, a model that is able to distinguish between dialects, is very good and capturing language identification model, which makes sense. But it doesn't need the full network to do it. It just needs 20% of its neuron to do it. So apart from that, we can also use this type of analysis for finding where this information are captured. As I said previously, from the layer, we noticed that the language information are predominantly present in the upper layer of the transformer network. So over here is an example. We notice that we need 50% of the transformers neuron to distinguish between 7 language. This is Mockingjay, but I believe with the Hubbard and others, we have better results. So it's an example. So over here, we have seen that mostly always the second part of the layer here is capturing the language information, and we just need 7.4% of the full networks neurons to have a significant contribution here. So this can help us to identify which part of the new network we can use, for example, for feature extraction or for doing fine tuning in any downstream task specific to this property. So this type of analysis can indicate which part of the network we can utilize it or not. Apart from that, there are other ways and other meaning that we can extract from this minimal neuron set. For example, using this minimal set and multitask for all the tasks that we did, if we compare, we already have the neuron IDs. So if we compare the intersection between the important neurons in each minimal set, we can notice, let's take an example of speaker recognition system. We can notice that in the last layer of the SRE model, that is FC2, 82% of the salient neurons is needed to capture the gender information. So if you remember, this is the only network where we need 50% of those neurons to recognize gender. Whereas it should be, we expected it to be redundant because the network itself was trained for identifying speakers. So what we saw is 82% of these salient neurons encodes gender information. And in the same layers, 50 to 75, depends on the language, the network is using to encode the voice identity that is being found by the speaker verification task. And 44% of that layer's neuron includes language information. So if we go over this, we see there is a huge overlap between the neurons that learns multivariant of this information. It learns gender, so some neurons learns gender, voice, language together. So this shows how the neurons can be and is shared by different properties. So this, just keep this in mind because this will be one of the limitations I'll come back to later on. So apart from this, we also see few other things. For example, we noticed so we have this tree information. We noticed that we have some neurons that exclusively get activates when there is a certain properties. So we call this, not we, let's say in literature, sometimes it's called switch neurons. So for example, in ADI model, when we noticed that we have instances that has female voice from Egyptian dialect, only that time that neuron gets activated. So this type of, not just one neuron, it's sometimes a group of neurons. So that group of neurons get activated. So this type of neurons, if we can identify, we can use it to manipulate. We can use it to manipulate certain behavior. So for example, if we noticed in a dialect identification, when there is a female speaker speaking in Egyptian dialect, the network gets biased towards it compared to a female speaker, let's say, speaking an Algerian dialect. We can use this set of neurons to manipulate that behavior and reduce the bias. But remember, we also have seen that there are networks that is shared among different properties. Whenever we are observing this switch, we are observing based on certain predefined properties. We don't know if this switch is actually related or being activated for some other properties that we are not testing. So if we manipulate this, we don't know what would be the reaction. So one of the biggest limitation of this task is here we are finding some neurons and saying, okay, this gets activated for this property, this encodes this information. This gives some insight, but we still don't know what happens during a prediction. What other variables are influencing the activation of this type of information? One example is, I exactly don't remember the paper, but there was a research on in language modeling, that they had a neuron that activates whenever someone gives input that includes horse. So they named it horse neurons. And over time, they always call it horse neurons. And if we don't want to, let's say, reduce any bias regarding that word, we can manipulate it. But when they increase their search area, they noticed that that same neuron was activating for cars also. And during that time, when they expanded the context, it was related to racing, not horse, not cars, but racing attributes. So this type of issues, we really have to be careful when we say, okay, this is the neuron responsible for this property, let's manipulate it. So yeah, that's one of the disadvantage. Maybe we could come back to this later again. Then we have different properties that shows the robustness of the network. For example, let's go back to this result. Here we noticed that this voice identity information is not included in dialect model. So we know that this model is invariant of speaker, so it's learning speaker invariant information. That is, it is not dependent, or it is not biased towards non-speaker. So why this is important, when this is important? For example, most of the data we crawl now, let's say for dialect, was from YouTube channels, programs where we have one host in many programs. And then when we, let's say, split the data for training and testing, most of the time we try not to have the same speaker, but it's not possible. So sometimes we do, there is a concern that if these models are learning something specific to a speaker. So for same person speaking in Egyptian, if that person is in the test set, will always give better result for Egyptian dialect. So in this case, we are actually being quite sure that, okay, this voice identity is not being captured by dialect identification. That means the model will be robust against unknown speaker. So this type of robustness we can also test in our property, using the neuron probing. I'll be very quick and finish, I think, 20 minutes. So potential application of this task, we can manipulate neural networks behavior. Yes, this is a potential application, but I already explained why this is very dangerous and why we have to be very, very careful regarding this. We can also learn model distillation and efficiency. Yes, we can, because looking into the results coming back here, we see that for, let's say, for language identification, or for example, for dialect, we need only 25% of the network's neuron. So if we can learn which neurons are redundantly encoding this information, we can remove it and decrease the size by, let's say, 75%. And that will actually help us for different reasons, computational and also for when using for embedded system. Apart from that, with all the speech representation models like 300, I think latest Hubert was 900 with 48 million parameters. We always don't need those huge architectures. Whenever we work for downstream tasks, we just picked few properties that those models should learn. So using this probing technique, we can identify those small amount of neurons and help use them to either transfer learn our models or towards domain adaptation, depending on what we want to do. Yes. And so limitations, all the method that I mentioned, first we used a very simple probe. It has logistic regression. There has been studies where people use random forest for this and use their purity to rank the neurons. And also there has been studies where people use LSTMs and more complex probe. So we used it for our, for the simplicity of it, and also to use to have a better interpretability. But yes, we need to also explore how the complexity of the probe influence the interpretability of the results. Plus, the technique that we mentioned, like a probing technique, is highly dependent. It's completely dependent on annotated data. So we need to have some manual annotation for finding, this is gender classification, this is let's say speaker information, this is the language information, this is dialect, this is emotion, these layers are encoding emotions and such. So this is really big limitation, that we need to know what properties we are looking for. We cannot uncover, like for example, using clustering, we can do some maybe novel concepts, but here we can't. Apart from that, as I mentioned earlier, these are just looking for a particular property at a certain amount of time. But we don't know how this interpretation is being connecting within the different neurons or interacting between the neurons during prediction. So we really have to find other ways to find such interpretation, like causality analysis. Then, with all this, there are still open issues. Given apart from these limitations, we know that neurons are multivariant in nature. And again, as I was saying, we ignore this interaction in the current method. So we really need to find out how to model this. And there is no standard way to evaluate or interpret these findings. So we have to find out how to understand these numbers and what to do with this. So I will finish over here. Sorry for quick talk, and please, anything you have asked and any suggestion, I would rather have it as a discussion. Thank you.
All right. Thank you for the great talk. If you have any questions, feel free to unmute yourself or put it in the chat.
Okay, chat.
I have a question.
Yes, please.
Thanks, Shammur, for a great talk. So I'm still new to this neuron level analysis, and pardon me if this question is too naive. So I'm wondering, how do like different training runs of the original model affect the results of the analysis? For example, we know that, okay, this is the neuron for English language. But then if I retrain the model, then, or let's say a better way is these 10% of neurons are the English language neurons. But then when I retrain the original model, does that percentage vary, or like how robust it is to that?
Yes, actually, that's one of the reason when we chose the data, especially for speaker verification, we use 3 languages over here to show. Let me go back to the result. Okay. If you see over here, whenever we use the same network trained on Voxelab 1, this English test set is Voxelab 2 official test verification test pairs. This we created from common voice subset of similar size for Chinese and Russian. So we also tested with other languages, but over here I'm showing just 3 of these. The neurons, the percentage of salient neurons or the minimal set actually differs 50 to 75%, But what we noticed in this 50%, most of the neurons are overlapping. So this other 25% of these networks, neurons are added for the English language, but yes, mostly they're common. So we can, again, as I said, these are all, we are speculating because there are maybe other factors that are implicating over here. So that's why when I'm saying 50% of these neurons, 50 are for speaker information or voice identity. So this is how actually it differs between language, and you can find the overlapping based on the neuron IDs, because whenever we are extracting the neuron ranking, we are keeping the IDs accordingly. So we have the neuron IDs for each set. So yeah, did I answer your question correctly?
Mm-hmm. Thanks.
Mm-hmm.
Hello, thanks for the very interesting talk. I also have some questions.
Please, yes.
So my first question about the probing method is that you use the average polling before you input the neuron activations into the proxy model.
Yes.
Don't you think that you lose a lot of information by just averaging everything?
Yes, of course. But at this moment, we wanted to study the utterance level. We did try different polling methods. Like, for example, when we tried dialect identification or the speaker identification, we did try with the, we tried statistical polling and other, but we didn't find any significant difference in terms of course, the number of neurons change, by the way. If we just do average pooling, if it is 100, if we do statistical pooling, we have neurons that are encoding the average and also the variance. So in this case, of course, the result changes, but the location of the layers and the amount of neurons we noticed is more or less directly proportional. So what we did is we tried to find the standard of pooling people used for the respective architecture. For example, for this dialect identification model, we noticed that whenever in the original network, for shifting from frame to utterance level, they use statistical pooling. So our main focus, or the result we presented, were using statistical pooling. Whereas we noticed that most of the downstream tasks, when people presented with Mockingjay, was either using average pooling. So for that model, we use average pooling to present the results. So yes, but exactly, your concern is really important, because it changes how numbers of neurons and what information it's actually keeping. So yeah, you're right.
Thank you. And I have a sort of follow-up question.
Sure, please.
So if I understand it correctly, you're building this proxy model and you're using the weights of the proxy model to basically assign importance to the neurons. But are you also taking into account the activation values of the neurons? So are you just using the raw weight values, or are you somehow calculating the contribution of that neuron with the weight to the output? So right now, the problem is that for me, at least, the issue would be that you could have a neuron which has a very, very small activation values, and the model could assign a high weight for that, and still it would have a very, very small contribution to the overall classification.
We are just considering, for this, we are just considering the model weights, but when we are, no, we are not thinking of it like this. We are doing the absolute values for the weight, both positive and absolute, because we want both positive and negative impact, but no, nothing other specific than that. So yeah, that would be another way to look into it. But sorry, yeah, please continue. You were saying something.
Yeah, I just wanted to ask whether you tested it, because I feel that maybe it would be better to use the contribution from one neuron to the output of the proxy classifier as a sort of importance score.
No, we are using the weight assigned by the proxy classifier when it's using the activation as a feature. So yeah, so the input
Yeah.
is the activation of the feature, but we are using the weight assigned by the model. Yeah.
And I think I saw in some other works that they actually use the gradients of the output with respect to the input. So that's another sort of way to calculate the importance.
Yeah,
So maybe you can try those two and see how the important neuron group changes, or if it changes at all.
Yeah, thank you.
Thank you.
So thank you for this talk. In fact, when I registered to your presentation, in fact, I was expecting something about latent spaces, because, you know, if you think about this neuron probing, there is no guarantee, in fact, that you really probe the latent space per se. Because it's at the end, it's a classifier.
Yes.
So, in fact, so you can think about, you know, this selecting neurons and so on. What could be interesting also, or a way, in fact, to think the problem would be to somehow to probe the latent space per se. So these neurons, the groups of neurons are somehow evolving in a latent space where you have representation. For me, a representation is representation in a space. So what could be, and the second problem is the fact that you have this proxy classifier. You apply a gradient descent. So each time you have you have no guarantee that this proxy is really robust. Did you perform, for example, 10 or 20 different the gradient descent to know if your representation or your choice is really meaningful?
Yeah, actually, I didn't mention, but we did, for example, we did experimented with different iterations and also seeds. So yeah, but no, we haven't specifically looked into the changes in the gradients while doing it. But yeah, we all these results were averaged of different.
I suspect that the numbers are the same, that each time you have a different set of neurons and so on. So, you know, we are with one of my students, we are examining speech generation system, so end-to-end TTS, to examine what are the latent space, or what are the intermediate representation which are built by the the text encoder. And we just perform a very classical LDA or something like this, which somehow preserve the initial space and just rotates in order to maximize Malanobis distance. So it's very alike your L2 and L2 and L1 and L2 constraints, where you have to you group, in fact, neurons that are participating to the same class, and try to distribute them in the latent space. And in this case, you have a robust representation because it's completely deterministic.
Yeah.
So did you compare these two kinds of approach?
No, we didn't. Yeah.
Because it looks very much more straightforward than, you know, trying to.
Yeah, it's actually very simplest form of probing that we did. We just wanted to see if this information is there or not. And also, can we just, for example, take very small amount of neurons for a particular task. So that's why it's one of the biggest, as I said, the lackings of it is whenever we're probing, we know what we are looking for. You have to know what you are looking for. We don't consider any other surrounding variables that can implicate or can affect this prediction. So yes, this is the biggest drawback. And this is, yeah, this was for just to see our model was robust against gender or channel information or not. So yeah, I think we should add more other implication that would consider.
Okay. Do you have an idea of the, how to say, of the latent space you are probing? Because if you have an extra, for example, you introduce an extra dialect or an extra speaker, how does it, how is it placed, in fact, in this in your representation?
I didn't mention over here, but we did some study. For example, when I said that for the dialect, we chose over here when we mentioned 5 and 4 classes, what we did, for example, the original model that we probed had 17 dialects, for example. So when probing, we first started with 4 regions that classifies those fine-grained into bigger chunks. Like, for example, North African dialects includes Algerian, Morocco, etc. And we saw the behavior of the network based on which layer or number of, amount of neurons needed to encode this information. And then we added another class. So we did this again in the shallow, very like upper abstract level. Then we added another class that's called Standard Arabic, which is not any dialectal, which is not a dialect of Arabic, but it's a standard way that people used in news, like a formal language. And our original pre-trained model didn't see it at all. So what we wanted to see how the, let's say, how the information pattern or the localization of the important neurons changed. But again, it was in the abstract level. And we noticed that before, like the feed-forward network were very concentrated for, let's say, for, were most salient in case when encoding the 4 dialects. But the moment we gave another information that was never seen by the pre-trained model, we noticed that the neurons, especially from the CNN networks, were prominent. So over there, the CNN was using as a serious feature extractor or feature provider, information provider, that the network or the probe could use to infer the 5th label. So we did tests like this, but not to a very granular level like you're talking about. So yeah. Yeah.
But yeah, so I think the question, perhaps a question you can ask yourself is, do you, by selecting these neurons, do you build some kind of a subspace where the dialects could be projected in a very smart way, which is meaningful in phonology? Or is that just a subset of neurons which are just able to distinguish between the dialects? So is that a building a space, a latent space, makes sense for phonology, for science, or is just a subnetwork which somehow just discriminate between your samples?
That we have to actually.
I think that's a concern about how using deep neural networks or statistical science, these new statistical tools to probe, to use it for probing data, to acquire knowledge.
Yeah. Okay. Yeah.
You know, for our natural brain or natural intelligence to improve.
Yes, absolutely. I mean,
artificial intelligence to the benefit of linguistic, phonology, and so on, to have a better way to probe data, to acquire knowledge.
I mean, yes, I mean, if we could actually relate, I mean, as I was saying, we could use it multitask. If we could relate, let's say, the content-based analysis, something like, let's say, phone recognition, with the dialect together and see how the network was behaving. I think maybe that's something I really would look into later. Yeah, yeah, it would have given better ideas. So you are right in that sense. Also, yeah. Okay, that's it.
Thank you.
Thank you so much. Yeah.
I'll jump in and ask maybe one more question. So there's this folklore almost circling around, self-supervised representation learning, that people believe supervised tasks tend to drop information as you go up in the higher layers.
Exactly, yes.
So are you observing the same thing?
I mean, yes, we did, but this wasn't with this experiment. For example, there was also another paper. So if I give a published reference, it was about what neural network hears, I think, right? Yeah, it was an ICAS. So they tried to probe a ASR model. ASR? Yeah, they tried to probe, I think, ASR model, and then read it with the TTS and probed with TTS. So yes, they noticed as we go up in the layers, like for example, if the lower layers keep to tends to keep all the timbre and every rhythm information along with the content. But if I remember correctly, as we go up, just the ASR was capturing the content information only. So in our case, we also noticed this. For example, we tried to create another downstream or probe task, as I was saying about phoning, but we didn't, I mean, officially finished it or something. We noticed that the more granular level we go, like the CNNs are better in doing phoning classification, for example, than the upper layers of any model. By any, it's here 4 models of them. So yes, the more abstract, all the abstract information are actually captured in the upper layers. And this is seen also here. If you see all the information that I showed, like probed for language, they are abstract level information. And most of the cases, we notice this information are localized in the upper layers. So I would agree with this completely, but this is what we have seen.
I see. And then I suppose for the self-supervised models, the information are, they can retain more information compared to the supervised ones, just because the objective is different.
Yes, of course. I mean, but at the same time, it's I wouldn't really rejected the previous CNN models that we learned. Because again, this was another, I'm bringing together from all the other parts that I didn't present over here. It's like if you compare the representation learned by, let's say, old CNN model that you trained for any objective, supervised using supervision, and just take the CNN layers, we notice that those CNN layers has the capability to capture representation as much as, let's say, for over here in Mockingjay. So I wouldn't say that the old CNN networks are, whatever they're learning is useless. I would rather reuse it. I mean, actually, this was one of the interests. I mean, this total work was a side product of another interest, as I was saying. The interest was to see, can we use previous, let's say, CNN layers for some other task? Yeah. So I would suggest not to discard those models. I mean, they're useful. So, just a personal opinion, maybe, yeah. Anything? Yeah, it's a 30 minutes of 1 hour.
I think we are running out of time. Well, and
actually, my objective was to learn from, I mean, so that I think I'm done. Yeah.
if people have more questions, feel free to unmute yourself.
I actually want to, I mean, if we have time, I want to put one question in front. Like, as I said, I'm learning it myself, so that would be great. I don't know if anyone have done it, but this is something I was looking into it. Like, we have different speech representation models, right? Now, I mean, as I was saying, the parameters are growing. We have, but most of the models, fortunately, we use, let's say, Libri 900 hours, 960 hours of data. So we give the same input and learn representation from it. But how much is the layers representation are similar between, have anyone, I mean, I thought this is something interesting to pose. And as we have a lot of people over here who did analysis on it, maybe they can, like, what do you think? How much representation are actually, anyone tested on this? I was thinking about this field as well.
Not to my knowledge, but maybe others can comment.
Like there, I think this approach is like multimodal search, like representation to do it. I saw it to be done for some NLP task, but it's not yet that popular. But yeah, that would be interesting. So yes, that was anyway. Yeah.
But I suppose if you change, say, your architecture, your training approaches, everything might change. It's just a question of to what degree it changes. Because if you're still using LibreSpeech, I mean, everything is in the data. So,
of course, yeah. I mean, but still, you are learning some representation that you want in future or in other tasks to transfer, right? So if we are learning, let's say, transformers, it's after CNN some transformers, there maybe our training mechanism or schema changes, but does the representation, I mean, shouldn't the abstract of that representation should be related? I don't know, it's just, sorry. I thought I had the time and brain full of people, so maybe I'm just...
Well, you can do alignments, right, of different layers. That's certainly interesting.
Simple correlation might be also a way.
You know, just a suggestion of an old guy. I think good questions have been already posed in the literature before 2000. So it could be interesting to re-examine questions which have been done by phoneticians or whatever, and use our new tools which are dealing with you know, big data and so on, to see if they were true or not. For example, where is the speaker identity? Yeah, for example, do nasal vowels carry more identity than oral vowels? Because you cannot vary the nasal cavity and all this kind of stuff. So what could be interesting is to revisit with the new tools, with the big data we have in hands now, the things which have been questioned with just a dozen speakers and a few seconds of speech. Let's say it could be you know, the handover between generation of researchers. Instead of trying to reinventing the wheel, it would be interesting to so the questions are very important. So I don't know the question about representation of data. I don't think it's a good question.
Okay.
Perhaps localization of information in time. I think I'm joining the question previously posed by Thomas. Where is the information in time and space about identity, about gender, about sense? So there have been already some answers in the literature, in the old literature. So try to revisit it with new tools, with cross entropy, with entropy measurements, new statistical tools, new ways, and so on. But the questions were good at that time already.
Thank you.
Just an advice, you know.
No, love that. Thank you.
See you guys.
Bye.
All right, I think we can stop here. Thank you so much again,
Thank-
Shammur, for the talk. And thanks for the lively discussion as well. Yeah, and I will see you next time. So well, I'm not entirely sure what we'll have next time, but we'll have unsupervised word segmentation talks, and then talks on unsupervised phonetic segmentation as well. So looking forward to all those. All right, I'll see you next time, guys.
Bye.